Hello everyone, my name is Sam and I'm going to be giving a talk about smart contract code size optimization, specifically beating the 24 kilobyte constraint. Some of you have probably never run into this if you're only dealing with relatively simple smart contracts, but the more complex they get and the more features you add, you're undoubtedly going to hit this. And I'm here to save you some of the agony that you're going to encounter and give you some tips on how to solve them. But before I do that, I'd like to introduce myself a bit more, because this is the first talk I've ever given, and there's probably a lot of people who don't know anything about me. So, I'm a software engineer at heart. I love building things. I've been a professional software engineer for almost 10 years now, and I spend the majority of my spare time programming on various projects, just because that's what I love to do. I've been fascinated by cryptocurrency for quite a few years now. Before I co-founded Paintswap, I was a senior protocol engineer for another cryptocurrency project, so I understand the fundamentals quite well. And unlike a lot of people, I am just here for the tech side of it. And on Paintswap specifically, I wrote pretty much all the smart contract code, as well as all the subgraphs and the API side. So what are we going to talk about? Well, for starters, what the current maximum contract size actually is, some things that should help in reducing it, and some things that might help, but they might not as well, and we'll go through some examples, and then we'll just do a rundown of everything we covered and some final conclusion points. And for any examples, I'm using Solidity 0.8.9, which is the current latest as of today, and I'm setting optimization and with a run of 1. So I'm assuming that the audience has some familiarity with Solidity in general. So we're going to be using Hardhat, which if you aren't using it, you can get here and follow the tutorial steps there. It's super helpful. And also install the plugin, the Hardhat contract sizer. So when you compile your smart contracts, you can see exactly what size they're going to be. And this is the options that you'll need to set to have that run. And then we'll just compile the code, and that will be the output. So we can see it's 0.06 kilobytes for this sample test. So when you come to deploy a smart contract, it cannot have a size greater than 24 kilobytes. So we'll take this contract, it's massive, trust me, and then we'll compile it, and oh no, it's above 24 kilobytes. And this is the warning you'll get, and it'll be in nice and red. It says it's a limit introduced in Spurious Dragon. This contract may not be deployable on mainnet. Consider enabling the optimizer with a low runs value, turning off reversions or using libraries. So those are some of the things we'll look at, but also a lot more. So let's see if we can get this down. So let's start off with a super simple smart contract, which just has one state variable, which is a public uint. And if you didn't know, making a variable public automatically creates a getter function for it. So it's essentially equivalent to this. When you compile the code on the left, you find that it has a contract size of 125 bytes, whereas the one on the right has 120 bytes. So by writing more code, we've saved 5 bytes. So let's look at why this is. So these are the opcodes for the function. I won't go through everything, but I'll go through some of the more important instructions. So the jump destination means that somewhere else in the code can jump to this instruction. Push 0 is pushing the number 0 onto the top of the stack, and the 0 in this case indicates storage slot 0, which is where our fee variable is located. And sload means get the value at the top of the stack, which is 0, go to that storage slot, and obtain the contents of that slot and push it onto the top of the stack. Now let's see the opcodes for the implicitly generated getter function for the fee state variable for the contract on the left. We can see that there's now an additional jump destination opcode. And I've highlighted in red all the new opcodes that don't appear in the function on the right. So there's actually now technically 2 functions generated, because a jump destination is typically the start of a function. So what's happening now is the tag 3 instruction will be called when the implicit getter is called. It's then going to push the tag4 location onto the stack, call the same push0 and sload, which is going to load the fee onto the top of the stack, and then it's going to jump to tag4 location and then execute the rest of the code. Why it does this, I'm not totally sure. So if you want to save yourself a few bytes, just write out the getter function yourself. But one thing to think about is, do you even need a getter function for this? If it's only used for developer purposes, there are ways that you can still read it from the blockchain, because even though something's private or internal, it's still publicly accessible, just not inside of a smart contract. And we're going to look at that now. So as I mentioned, state variables are stored in storage slots, and each of these is 32 bytes wide, or 256 bits. So here's a contract with two state variables. They're both private. So the first variable, fee, will go into the 0 storage slot, followed by each other variable. So in this case, it'll be storage slot 1 stores some var. And even though these are private, you can still access the contents of them with ethers using the getStorageAt function and the equivalent in Web3. So if you're creating getters for these for the sole purpose of being able to read them from a developer perspective, you need to think, do you even need to? Because these are adding bytes to your contract deployment. So for things like the fee, I would argue the public should be able to easily access that through like FTM scan. So for that, I would make a getter function for that. But for anything which you as a developer can easily access, then I wouldn't. Unless you've got spare contract size, then why not? So one of the things about storage slots is that you can actually fit multiple variables together into the same one if they fit. So in this case, we've got a contract that has a uint 128, 256 and 128 again. But they're put into the order that they're declared in the contract. So this is actually going to take up 3 storage slots. So if we take the same contract and switch these two variables around, so we've got the 256 first, followed by 228-bit variables, you can actually fit those two into the same storage slot. And this is going to save you 32 bytes. So you want to think about the order in which you declare state variables. And also, if you can put commonly used ones together, then that will be more efficient gas-wise as well, because you only have to read one storage slot to get access to multiple variables. So let's take this contract, which has 2 events declared, followed by 2 variables, a constructor for setting the variables initially, and 2 setter functions, which are going to emit the events when the value is changed, and then just a getter for one of the variables. So when you compile this, it's 483 bytes. But what if we remove the event declarations and the emitting of them? Well, that gets us down by a third. So to take anything away from this, it's that event emitting is quite expensive. But we're going to see how we can keep the same functionality, move it to another contract, and get this marketplace one a bit more leaner. So this contract is essentially the same as the other one, it's just called something else. And this is that same marketplace contract which has now replaced all that functionality it had before and is storing the address of the other contract, the NFT discount. So we're setting that in the constructor, and then our getter is just calling into that other contract to get the discount. And all the setting is now going to be handled by a completely different contract. And this gets our contract now down to 283 bytes, so we've reduced it by 200. So we're going to do the exact same as we did previously, but with only one variable instead of 2. So there's only one event emitted, there's only one variable, and one setter function. So we're going to move it into a new contract and call it in the same way we did previously. So this is still 283 bytes, but the previous code was now 236 bytes. So we've actually increased our contract size by moving it into a new contract and calling it, because there is a overhead cost of calling another contract's function. and that has outweighed the doing everything in the contract itself. So in this case, it's only beneficial for us to move the contract to another one if we had two variables and two functions, two events being emitted. So yeah, it's something to keep in mind. When you're moving stuff out, it might not actually help at all. One of the suggestions I often see online is if you're creating a modifier, is to move the contents of the modifier into a new function, because the modifier itself is basically copy and pasted into any function that is using it. So let's see how that looks. So we're going to create a contract that has an owner state variable, which is set to the constructor creator, message.sender. We're going to create a modifier called onlyOwner, and that's going to check that whoever is calling it is in fact the owner. So we have an aptly named function mustBeOwner, which is using the onlyOwner modifier. So let's move the contents of the modifier into a function. So we've created a function checks is owner, and we've moved the requires clause into it. Let's see how the bytecodes look. So without using a function, it's 206 bytes, and using one is 215 bytes. So we've actually increased our contract size by following this advice. But this is because creating a function adds some overhead, as we've seen before. So in this instance, it's not beneficial to create a function, but we'll see a place where it is. So we're using the same contract as before, but we've added an extra function, mustBeOwner2, which is also using the onlyOwner modifier. So if we use the same procedure as before, where we take the contents of the modifier, move it into a function, checks is owner, and then calls that, we find that the deployed bytecode for not using a function is 278 bytes, and using one is 245 bytes. So we've saved 33 bytes by following this advice. And this was only because we're using two functions with the modifier. With only one, it wasn't worth it because of the function overhead that we saw previously. So one of the common implementations of Ownable is by OpenZeppelin, and this is what a lot of people use. And if we have a look at the code, we find that their onlyOwner modifier does not use a function. So we will not get the contract saving benefits by using them. We'll have to implement it ourselves. So using dynamic storage types like string is actually quite expensive. If we take this contract, which just has a function with a requires clause that's passing in the string hello, the deployed contract size is 219 bytes. Take the same contract, remove the string, we find it's only 167 bytes. And this is because of how strings are ABI encoded into functions. So that even though we're passing two variables, it's actually taking up an array of 4 32-byte numbers. So the first one is the Boolean expression we're passing in. I've just set it to true, just so that there wasn't loads of zeros. The next is the offset of the string into this array, which is 64 bytes. This is all hexadecimal. The next one is the length of the string, followed by the actual string contents itself. So the string is taking up 3 32-byte size in this call. So following on from that, let's create a contract called marketplace. It's got a function makeBid and another function called checkBid, which is going to check a load of the preconditions before you actually try to make a bid. So it's going to check that the bid is higher than the current bid, that the sale hasn't ended, that you aren't trying to bid on your own item, and there's a load of other checks that you might want to do. But as we saw, the require clauses with strings are quite expensive. So let's see how we can lower that. So what we can do is move it into a library, and then import that library into the marketplace contract, and then makeBid will just call that function. One important thing to note is that the library function should be external, otherwise they are embedded in the contract and you don't actually gain any contract size benefits. And because libraries use delegate call, we can use things like message.sender inside there, and it will still be the same as if make_bid had called it. So that's one of the benefits of using libraries. But you need to know that if you're using external in a library, you need to then manually deploy it and then link it into the contract. So this is how you do that with ethers, for instance. So for all the examples that I've shown in this talk, I've used the optimizer with a runs setting of 1. And to set the optimizer in Hardhat, you would update the config file like so. A common misconception is that the value for runs is how many times the optimizer is going to run, but that's not actually the case. What it means is how many times you expect the smart contract itself to run. So a higher value would tend to more gas-efficient code at the expense of contract size. So a lower value would give you a better contract size for the deployment, but not necessarily optimized for gas usage. So I thought I would put the optimizer to a test, and I ran it through a very complicated smart contract that I was always hitting the smart contract size limit for, and I used a different number of runs for it, and this is the results I got. So kind of a very low number of runs, like 1 to 10. It started off at 23.8 kilobytes, and then as expected, up to about 50 it was increasing. But then it reached the point where I was actually going down, and then for some reason around 300 to 320, it went down dramatically, and it was at this point I was actually able to run my smart contract efficiently. I don't know why, but 320 seems to be a better number for me than the default 200, so it gives you a smaller contract size and a better gas optimized code. So for this particular contract, 320 was the optimum, and with no optimization it was about 40 kilobytes. So using the optimizer with any number of runs is a lot better than not using the optimizer at all, so make sure you're using it. So what are some of the things we've covered in this talk? Definitely use the optimizer, and also play around with the runs values. It might surprise you, especially at the lower end. Move functions into a library. Make variables private and create your own getters for them. Or, if you don't even need the getters, don't use them at all and use the get storage functions. Like you can use in Web3 and ethers. And where appropriate, refactor out some code to another contract, but only if you're taking with it things like event emitting and extra functions, because otherwise the cost may not be beneficial. And for more advanced reading, there's the proposal 2535, which is the Diamond's multifacet proxy. This gets into a bit more complicated territory, but it's also, if you plan on having an upgradable contract where you can add and remove things, this is definitely something to look for. But it's going to add quite a lot of complexity to your contracts. And thanks for watching, everyone.